Hello, this is the 7th lecture in the series of lectures in typology for the beginners. And here today we'll be discussing rolling friction. I think it's a very important topic, both in science and engineering. And it has been researched and discussed over centuries, both in theoretical and in experimental methods, to come up to the reason why rolling friction is smaller compared to the sliding friction. Rolling friction is smaller and in many cases negligible compared to the sliding friction. That's a common experience in our life, everyday life, and also in engineering. And this has been observed by the ancient civilizations, and this has led to the invention of wheels. Now we look at this in a little bit more detail. As I said, that is a very involved topic, and obviously we cannot go into the very much detail, but we'll try to see as much detail as possible for the beginners. So we see here a spherical or cylindrical object rolling over a flat surface or even a curved surface on the left-hand side. And on the right-hand side, we see a block moving over a flat surface in a sliding mode. Now, if you consider the rolling, there are two very important aspects. Very briefly, rolling friction is small, provided it is a rigid body. If it is not a rigid body, there will be deformation at the contact surface, and this deformation will lead to sliding. And the sliding would contribute to friction. So the first condition is that it has to be a rigid body. But of course, in reality, that is not possible. And that leads to some amount of friction. But assuming a rigid body, the second consideration is that when rolling takes place around a instantaneous center of rotation. Now, this instantaneous center of rotation obviously moves around, I'll just show you in the next slide, moves around the circumference of the roller. And hence, there is no slip, and hence, ideally, there cannot be any friction. So, if you consider a spherical or cylindrical body rolling over a flat or curved surface, ideally there will be negligible or no friction. Whereas if you take a sliding, then there will be some frictional force depending on the combination of the material and the force and other parameters involved in it. So we conclude here that rolling over a flat or curved or any other surface would be smaller compared to the sliding of an object on a flat or curved surface. As we said before, that this is a very important realization, and earlier achievements in civilization have somehow come to understand this, and they have invented rollers and wheels. So in this respect, I'll show you a small picture taken from the book of History of Tribology from Professor Duncan Dawson. This shows the Assyrians positioning a statue at Kaunzik, which is probably someone like near Iraq in the present day, 700 BC. It is interesting, this picture, and that's why I have chosen it. We can see that a series of rows of people are pulling it with ropes tied to the statue in different directions and trying to put it erect as well as slide it. But at the same time, if you look at it carefully, you can see some small logs lying here and there all over the picture. Many authorities think that these logs are used as a roller underneath the sliding surface to ease the movement. I think some of the rollers can be seen under the statue. So this shows even the earliest or very early civilization have realized that rolling is definitely a much easier option to reduce the friction. And even in this picture, we can see the wheels, a cart with wheels being pulled by several people carrying some load. Okay, so this establishes that rolling is gives negligible friction given other conditions are met. Now we go to rolling friction first, and the types of rolling friction. Obviously, there are many different types of rolling friction, but here we'll consider mainly two. One is rolling friction, where there is some amount of slip or sliding occurs, probably due to the mechanism itself. If we look at the left-hand side, the railway track and the wheel. Ideally, the roller should roll over the track without any friction, but that doesn't happen. In automobile or railways, there is considerable horizontal traction felt, and this behavior is complicated, and obviously much research has been carried out and remedies have been found out, but amount of traction can be reduced but cannot be totally avoided. If you consider the space between the tracks, the figure shown on the right-hand side, extreme right-hand side, and in the middle, you can see the wheel falling between the two tracks. Now, in this position, the wheel rolls as well as slips. This is something that I think we can understand it very clearly, because there is no continuity, and hence complete rolling cannot take place, because for complete rolling, we need instantaneous center of rotation, and that cannot happen. There is another type of rolling where there is no slip. Ideal condition where rolling takes place about the instantaneous center of rotation, as we have seen it before, of the instantaneous center of rotation. And in this condition, obviously, ideally, there should not be any friction or very small amount of friction. Then there is free rolling. Now, here we discuss two different ranges of rolling. Again, free rolling means ideal rolling where there is no slipping. We can broadly classify this into two broad ranges. One is in the plastic range, other is in the elastic range. And the plastic range, of course, will depend on the type of metal, load, and other factors. But given all the conditions are met, then if we take two flat plates and put a roller in between and slide one surface over the other, very soon we'll see that a groove will be formed on the surface, inside surface. Now, this groove will be created in the first traversal itself. Again, I emphasize that this will depend on the type of material and the load, but provided these two are met, the groove will continuously increase with a repeated traversal. So as the groove becomes larger and larger in width, the friction force will come down. The right-hand side shows the groove and the groove width. With a repeated traversal, small d will increase, and we'll see a decrease in friction force. Now, there have been many experimental work on this, and I quote some of this. These experiments show that rolling force increases with increase in load. That's obvious. Load increases, and we need to apply larger force for the rolling to occur. But interesting thing is that the rolling force decreases as the ball tire increases. This again is fairly obvious because as we have seen it in the previous slide, that the groove diameter increasing gives smaller force, rolling force. So obviously, larger ball diameter will give larger groove track, and hence rolling force will decrease. The same results have been plotted on the right-hand graph, where the same thing is shown. Rolling force is decreased with the ball tire, and it decreases with the load. With these observations, people have correlated frictional force with the load and the ball diameter by the following equation. F is equal to K times W to the power 3/4 divided by capital D. W is the load and capital D is the ball diameter. And K is a constant, which obviously depends on material. As I said earlier, that this grooving would depend obviously on the type of material and load. As we said earlier, that with repeated traversal, the track increases continuously and the rolling forces reduce. But there is a limit to this. After some point, the increase in groove track slows down. There may be many reasons, but one of the reasons is the work hardening. And as that happens, probably it happens after 8 to 10% of the increase of the track radius, the slowing down or the equilibrium position is reached, then we can represent the above equation in the following form, where we say F is equal to K times W to the power N divided by capital D to the power M. N has been experimentally found to be 1.7 and M to be found out 1.85. And K is a constant depending on the material, as we said earlier. So this is a very nice small equation, useful for both scientists and engineers for developing ball bearings and other situations. So now we go to other part of the free rolling, where we say that the rolling of metal is in the elastic region. So here we consider that there is no considerable permanent deformation, that means indentation or grooving. And in this case, there are several theories to interpret this. First theory is interfacial slip. And the slip we have discussed earlier is always a culprit in rolling, because if rolling occurs alone, friction force must be small. But slip comes in and increases the friction. Then some scientists have proposed molecular adhesion and also elastic hysteresis. Let us have a look at it one by one. Interfacial slip. Reynolds in 1876 carried out some experiments with dry rolling with rubber surface with a metal cylinder, of course, loaded metal cylinder. And he found out that the cylinder moves 10% less than 2 pi r. How can that be? That is only possible if there is a slip. And of course, a slip in the macro scale, but if we talk about the smaller interaction or smaller interfacial contact, then it will be micro slip or even nano slip. So obviously, Reynolds' experiment proved that there has to be some slip to contribute to the rolling friction in the elastic ring. Similarly, Heathcote in 1921 carried out experiment with a sphere rolling on a groove. Now here obviously we can see that the band AB the central band, must be larger than the band outside CD. And if that happens, for the whole sphere to move as a single body, there has to be sleep, because AB is larger than CD. So this, of course, leads us to the conclusion that there will be sleep even in the grooved surface and with the spherical body. So these are the two nice experiments to show that there is more sleep. Now, there was another very interesting experiment done by John Goodman in the University of Leeds in 1987, just after Reynolds. And he too observed that, if you look at the figure on the right-hand side, then he found out that A, that is the central radius, is larger than A1 and A2. Again, for this to happen, for this to roll, there must be sleep. So all these three experiments goes to show that for rolling to occur without sleep is difficult in the elastic ring. And then there, some sleep comes into picture and contributes to the rolling friction. Tomlinson in 1921, much later, considered that sleep is not enough to account for the amount of rolling friction that we usually find. So he proposed that there must be some molecular adhesion between the rolling surfaces. But here, although this seems to be a very plausible proposal, but one must remember that the molecular adhesion to be operative, the surfaces have to be very smooth and clean, as we discussed in the last lecture. And also, it has to be in the atomic or nanoscale. In the macroscopic scale, it will be difficult to realize the molecular adhesion, because there the two impeding features are the surface roughness and the cleanliness. Cleanliness is, of course, very different, very difficult to find out, to observe. So Tomlinson's theory seems plausible, but there are difficulties there. Then finally, we come to elastic hysteresis in rolling. I think this has been widely accepted, and people consider it quite often as an important contribution to the rolling friction. If you look at a roller rolling on a surface, with a compressive load, then the raceway or any other surface of the material in the forward portion will undergo a compression, obviously. And the trailing surface will be released. So this leads to what we call elastic hysteresis. And if you look at the figure on the left-hand side, the stress strain diagram, we can see that initially stress increases linearly or slightly non-linearly, depending on the type of material, increases to some point. And if we reverse or release the load, then the load may not follow the unloading path, may not follow the loading path, even in the elastic range. This is because of hysteresis. And if we go to the negative axis and then go on loading, we'll see that it will produce a hysteresis. And the area covered by the loading and unloading path is the energy loss. And this energy loss is a contribution to the friction. And in addition to this, if you look at the figure on the right-hand side, there is a little hump on the forward portion of the rolling surface. And some energy has to be spent to go over that hump also. So obviously, this will add to the rolling force. So this is an accepted theory for the increasing rolling friction, because normally we consider that rolling friction is nearly zero. And many rolling element bearing manufacturers claim that their component is zero friction, but that is absolutely not true, because there are the reasons showed earlier, and here the hysteresis loss can be significant, and we cannot have a zero friction. So we complete it here today, and we'll start a new topic next time.